Hello everyone, welcome to the third video. This is a video on basically what we were talking about before. It's CPUs, and what I wanted to do was go through what the CPU at a lower level looks like, so what the problems are and all this sort of stuff. I appreciate this is quite in depth. I hope that it's relatively simple to follow. So but bear with me, things will start coming together. I'll do this quite a lot where there's a lot of information, but I will come back out and I'll look at the bigger picture, and we'll have a see globally what's happening. We'll have a see on the markets and desktops and all sorts of things. So we will get this. We'll get the picture of this. So let me get stuck in. We spoke before about how the efficiency of a circuit is a very, very useful thing, and the manufacturing of these simple things. So we've got let's say several. This is a big board of it, and what I mean by a big board is we get like this slate, we get this chip, a huge piece of, let's say we get this huge piece of silicon metal sort of thing, and then in the factories they will basically create some kind of mineralization over it. So imagine if I poured water onto this. If I poured water all over this board, and let's just say it was a board of metal, right? Let's just say it was stainless steel. If I poured water all over it, but it was saline solution, this water had a lot of salt in it, and I just allowed it to dry. I just left it on a flat surface and allowed it to dry. Once all of this the water actually evaporated, what would be left? Well, what would be left is actually, let's do this in a magenta kind of color. What would be left is this kind of crystal board, right? There would be loads of crystals of salt left on this board, and very, very small. Impossible for us to precisionally make this like that. Now this is a similar thing. I don't want to go into this too in depth, but this is a similar way we make CPUs really. So we get this board, and the manufacturing processes, they pour some chemicals onto it. They pour some. They might sketch in something. So they might sketch in these buses, as they're called. We'll go through those shortly. And if we have these buses, if we have these things that are sketched in, so it might be lasered in, or it could be, it's not really drawn on. They're a bit too small for that, but they could be lasered on effectively. And we'll talk about buses, don't worry. So we pour this stuff on it, and this bit evaporates here. This bit evaporates here. This bit evaporates. All of this evaporates here. And perhaps we've just tipped molten metal on or something. But the beauty of this is these tracks here have stayed the same. There might be some metal conductors or something of the sorts. So that's effectively what's happening. So as this is evaporating, it leaves the residue here. It's sort of mineralized over here, and it's quite a fascinating way of doing things. But this is effectively how these CPUs are working. So going back to this salt definition of it, is, well, these circuits are very small. We're creating CPUs, we're creating these chips and boards in very, very small ways at the moment, which are microns. They're too small. They're like atomic level type thing at the moment. Now when we have a CPU at the moment, there'll be some calculation-y things here. I won't go into these too much just yet. I'll go into them afterwards. But this is effectively what we're trying to create. So now we can create circuits with this. So these are mineralized things here and here and here. These transistors would be mineralized. And what they're doing effectively is creating, allowing things to flip, allowing things to, which we'll go through in a second, but we're allowing calculations to happen. Now the problem is at the moment is that they're really, really small. They're so small that they're sort of atomic level, and the problem with that is that there's something called quantum ghosting, and effectively what this is doing is the electrons in these atoms here, they perhaps there's walls put up in place here so they can't jump easily. Well, actually what's happening is that the in quantum mechanics, which is just the area of physics that studies very, very small things effectively, the area of quantum mechanics says that actually the law of physics suggests that electrons are allowed to basically walk through walls, hence why it's called ghosting here. They're literally ghosts, right? So you can see the problem with allowing these electrons. If I want this electron specifically to go here and then here and then here and here and here and here and come out to here and go out like this to create a circuit, remember we had this circuit. If I wanted the electrons to do that, but this electron here, let me do this in blue. This electron now here decides I'm going to walk through this wall and I'm just going to jump over here instead. That's a problem, right? Because we can't control a computer anymore. So effectively, this is the scale I'm talking about. The main take from this, if this is too much, but the main take from all of this is that they're incredibly small, but they are very, very intricate, and this is why we can actually physically do billions of calculations per second. So I didn't want to just say, let's get back to a CPU in general. You might see a CPU and you might see this 2.6 gigahertz. Well, I didn't want to just say CPUs come in this size and they come like this, and they're i5s and they're i7s and they're M1s, etc. I wanted to show you what these mean. At the end of this short section in computers, we are going to pretend to buy a computer. We're going to buy a laptop, and I'll go through in some detail every single point. So if you do want to buy a laptop, or if you do want to buy a computer, you'll know what all of the specifications mean, basically. I think that's a very important tool to have for anyone anyway these days. Right, so going back to this. Remember I was saying that they are very, very small. Things are happening at the atomic level. They're happening with electrons. These things are incredibly small. I can't stress that enough. And I also said that it runs at roughly the speed of light. So if I have a chip that's probably about this size to scale, obviously depending on what you're viewing this on. If I had a chip this scale, and I had loads of circuits here, loads and loads and loads and loads and loads of them at the atomic level, right? There's going to be loads of different types of circuits I can create. Now, on top of that, the actual physical distance. You know, if I go 10 miles an hour for 1 hour, so let's say that this distance is 10 miles. Let's say that's 10 miles, or 10 kilometers, I should really say. Yeah, let's use kilometers. Let's get off miles. Right, 10 kilometers, and I'm going 10 kilometers an hour. So 10 kilometers per hour. That means I'll get there in 1 hour, right? And it's a similar principle. That's a slow speed. So this wouldn't be a very good speed for CPUs to run, because it would take so long for the processing to be done. Anything that a computer can do, we can actually do by hand. There is no maths, or there's no processing that a CPU can do or a computer can do that we can't do by hand. So effectively what this, I'll cut it short after here. I'll cut the video off in a second, but once we appreciate the distance of these things, we can realize now that actually this 2.6 gigahertz, and giga means billion, and hertz is a frequency effectively. So that means that this CPU is doing 2.6 billion calculations per second. So a hertz is per second. That means it's doing 2.6 billion gigahertz per second, effectively. Calculations or cycles or frequencies per second. That is an insane number of things. That is an insane number of calculations if you think about it. And we can do that many purely because of the distance between these things. So we've got the distance and the speed of light nearly, and we can create things at 2.6 gigahertz. I think my computer at the moment is probably running around about 2.6. That's 2 to 3 or 2 to 4, somewhere between that is roughly the amount. Now you can. The last thing I wanted to say before I cut this video off is I hope you can appreciate that there would be some kind of limit, right? The speed of light is very fast, but it's still limited. So surely on a chip that's this size, it would physically take so long for the electron to get from one point to the other, which means there should be a physical limit of how many calculations a CPU does. In the next video, we'll carry on looking at CPUs. Thank you very much, guys.